Hey guys, welcome to the Minute Show. I'm Tanay here. I would like to thank my friend Ayush for helping in the previous video balancing chemical equations using algebra. So we're going to be learning about vector resolution today. Okay, so let's start by drawing up a vector. We'll draw it as an angle of 37 degrees. Okay, so it's 37. Yeah. Let's draw up a vector. Now, as you all know, a vector is represented by an arrow. Now, the length of the arrow represents the magnitude and the direction obviously represents the direction. Guys, I'm going to keep it really basic and simple so that you understand it. If you want the complex things on that, I can make another video, but for now I'm going to keep it really easy and simple. Okay, so let's say that this is a force which is being applied on the plane, our frame, which is the plane for this vector. We have a force which is being applied on this plane. Now it'll displace this plane, right? If you, or let's say you have a paper and you're pushing it with your hands will displace the paper, right? And similarly, this force, even if you apply here or you apply it here, it more or less means the same thing. So we can apply it anywhere. Let's erase that. Now let's first understand, why do we need vector resolution? A pretty simple case, let's say we have a wall, or let's say it's a ground, and you have a box with the center of mass here. Now let's say you are pushing the box, you're pushing it like this, or to make it more systematic, we can, let's say the force is being applied in this way. Now, as you all know, that some part of the force will be pushing the box towards the wall, and some part of it will be pushing the box along the wall. Now we want to know what is the force which will push the box along the wall. Now let's clear this out, that it's pretty stupid if you push the box that way, because you're going to get some part of it wasted, and that's what we'll get. So what we're going to do is, we're going to take the scale, drop the x-axis here and the y-axis. Now, as I said, a part of it will be on the wall, and that's called a component, which means a component of the force will be acting in the x-axis, and a component of it will be acting on the y-axis. Now the component which is acting on the y-axis, that is towards the wall, in this direction, will be wasted, right? It won't have any effect, it won't displace the box. What we need is to displace the box, so we're gonna take this force. Now we'll see how to get them differentiated into these two components. Okay, let's drop a vector again, this time at an angle 37 degrees again. 37, yes, 37. That's our vector. Okay, now let's draw up the y-axis. axis now. Now what we need is the angle first, which is theta as we call it, and here the theta is 37 degrees. So guys, it can be radians also, but you have to convert it back, right? So we need to know what component of this force is acting thiswards in this direction, and what part of it is acting in this direction. Now guys, I told you the use of this method, right? Because it will help you understand it much better, and you will get interest because it will feel like a power to you that you can do this, right? That's stuff. So let's see. Now we have a vector drawn up here with its two components. It is the y component and it is the x component. Now we need to calculate the values of these, the magnitude, because we have the direction, right? So let's get into the math. Okay, as we all know, if we have a right angle triangle, sine theta is equal to P by H. So that means the P is gonna be equal to H sine theta. So we're on the same ground as that. Okay. But that was the y component, as you all know. The perpendicular is the y component. Now let's say we need to take out the x component. What to do? Now we all know that cos theta is base by hypotenuse. So that means the base, which is the x component of this, is h cos theta, right? Now we go from that. Now let's learn how to apply it. Now in this case too, we can do that. What we'll do is we draw a line. You know, guys, as I told you, we can apply the force anywhere on the plane. So the y component of this force can be moved from here to, on the screen, idiot, here. That's the same thing. Okay, now as we see, we have a right angle triangle. This angle is 90 and we have a theta. Now let's say it's force, and that force is, let's say, 10 Newton. It'll make things easier. Now the y-axis is the perpendicular, as you all know, so it will be h sine theta. Now h was our original vector, so let's clear the screen up a bit. I'll remember theta is 37. You guys should also. Yeah. So h sine theta, which is 10 into, now sine 37 is 3 by 5. Now that's because if you draw a triangle with the angles 37, 90 and 53, the sides will always be in a ratio of 3, 4 and 5. 3 being the perpendicular, which is when the theta is 37, that means the side opposite to 37 will always be 3 and the side adjacent to 37 will be 4 and the hypotenuse will be 5. Now the sides will be in this ratio, and as we all know that sine theta, cos theta, tan theta, and all the trigonometric ratios are ratios, they're fractions, so they cancel out. So they're in we don't care they're in any value, they have any value, they're gonna be in the same ratio. So let's get to the calculation now. It's gonna be now 5 and 10 cancel out, this becomes 2, so it's gonna be 6 Newton. Now h sine theta, which was y-axis, is 6 Newton, and now for the x-axis. Now x-axis, as you all know, is h cos theta. Now what is h cos theta? H is 10 Newton, so 10 into cos 37, which is 4 by 5, becomes 2, and it's 8 Newton. So this becomes 8 Newton, and that's what we call vector resolution. Yeah, you resoluted that vector. Now you know what effect it's gonna have on the x-axis as well as the y-axis. Now let's get up to the practical example of that. How can we apply this to the practical world? Let's get back to our original example. Ooh. That's a big eraser, huh? What color? Black. Okay, let's take up our original example. We have a wall, we have a box on that, and we're applying a force. Now let's say this force was 8, no wait, let's take it as 10 only, 10 Newton, and it was at an angle, let's extend it a bit, of 45 degrees from the ground. Now we want to know how much force will push this block along this direction. So we can do the same thing now. Let's resolute the vector, make it a bit less messy now. Will we draw it? Oh wait, kill these lines, take the box, draw the vector. So we have 45 degrees. Okay, so let's drop the y-axis. And the x-axis. Okay, who did that? Now the x-axis is gonna be the ground only, right? Yeah. So as we all know that theta was 45 degrees, our vector was 10 Newton, so this one's gonna be 10 into sine 45, which is 1 by root 2, so it becomes 10 by root 2. What's that gonna be? It's gonna be 5 root 2. So which means this vector is 5 root 2 Newton, and this is 10 cos theta. So that's also, as you all know, is cos 45 is 1 by root 2. So this component is also gonna be 5 root 2 Newton. Now let's make it a bit more interesting. Now let's say you knew the mass of the object. Let's say it was 5 kgs. Now you want to know with what acceleration it would go. Now that's easy. We all know that F equals mass into acceleration. So we have the force on the x component, which is actually pushing the box, 5 root 2. We know the mass, which is 5 kgs, and its acceleration. So 5 cancel out, and that means a scale. We get off. That means A is root 2 meters per second square. Wow, you applied a force in some other direction, you had the box moving, and now you know with what acceleration it would go. See, that's what physics does. Thanks for watching, and stay tuned for our next videos. Subscribe to know them instantly. Bye bye.